Hello everybody. In the last lecture I discussed about tangent plane and normal line of a surface at a given point. Then we discussed about linearization of a function, and finally we discussed about the expansion of a function by using Taylor's theorem. In this lecture we shall discuss about maxima and minima of a function. Then we shall discuss about a method of finding extreme value of a function by using Lagrange method undetermined multipliers. So first we define some local maxima and minima for a function of two variables. Let z is equal to f of xy be a function of two variables defined on a region R containing a point a, b. Then a function is said to have a local maximum value at the point a, b if the value of the function at ab point is greater than or equal to all the remaining value of the function at all the remaining points in the region. That means f at AB is greater than or equal to f of x comma y for all x comma y belongs to the region. Now we define the local minimum value for a function of two variables. So let us have one function z is equal to f of xy defined in a region R, and this region contains one particular point, say AB. Then a function z is equal to f of xy is said to have local minimum value at the given point AB if the value of the function at that point is less or equal to the value of the function at any point of the region R. That means f at AB is less or equal to f of xy for all xy belongs to R. So this way we can find out the local minimum value of the function. Now we define another term, critical points. Let z is equal to f of xy be a given point, given function of two variables defined on a region R containing a point AB. Then a point a comma b is called critical point of the function if the value of the partial derivatives with respect to x and y at the given point AB are 0. That means del f by del x at AB is equal to 0 and del f by del y at point AB is equal to 0. Or in another case, if any one or both of the partial derivative does not exist, then we can say that the point AB is a critical point for the function f of xy. Now we define a saddle point. Let z is equal to f of xy be a given function of two variables defined in a region R, and R contains a point a comma b. Then a critical point a comma b is said to be saddle point for the function if function is neither maximum value nor minimum value at this point AB. Now we want to discuss about a method of finding maximum value or minimum value, which is known as extreme value. Extreme value means either it is maximum value or minimum value for the function, and we want to discuss about a method of finding extreme value of the function of two variables. So we start with a function of two variables. So let z is equal to f of xy be a function of two variables defined on a region R containing the point AB. So first we decide or determine the stationary points or critical points for the function AB. For that we find the partial derivative of function with respect to x and with respect to y, and solving those two equations for x and y and find out the value of x and y. That means del f by del x at AB point is equal to 0 and del f by del y at given point AB is equal to 0, and then we find second order partial derivative, which are del f by del x square, then del f by del y, del square f by del y square, and del square f by del x del y, and find out the value R, S and T, which are second order partial derivative at given point AB. So let us denote R as del square f by del x square at the point AB. T is equal to del square f by del y square at point AB, and S is equal to del square f by del x del y at the point AB. Now, depending on the condition on R as T, we can determine this point is either maximum or minimum value or any other point. So let us check the condition. The function has a maximum value at the point AB if RT minus S square is greater than or equal to 0 and R is less than 0. Second case is function has a minimum value at the point AB if RT minus S square is greater than or equal to 0 and R is greater than 0. So for maxima and minima, both the cases, we have the condition RT minus S square must be non-negative or greater than or equal to 0. So if RT minus S square is greater than or equal to 0 and R is either positive or negative, or even we can put the condition on T also. Here we can check whether T is less than 0 or T is greater than 0. This case. Here we can observe that R and T must have the same sign. We can check it and we can observe it in the examples also. So here we can write the condition that either R is less than 0 or T is less than 0. Okay. Now the third case, the function has a saddle point. That means function does not have extreme value, or it is neither maximum nor minimum if RT minus S square is less than 0. RT minus S square is less than 0. The test is inconclusive if RT minus S square is equal to 0. Here the condition we have to improve is this RT minus S square is purely greater than 0, not greater than or equal to. So this is the typing error. Okay, now I come to the third case. The function has a saddle point at AB if RT minus S square is negative or less than 0. So if RT minus S square is less than 0, then the function does not have an extreme value at this point AB. Okay, fine. So, and this test fails or inconclusive if RT minus S square is equal to 0, and we need to find, or we need to use another method to determine the behavior of the function at this point AB. Let us take one example of finding maximum or minimum value of the function. So first example, find an extreme values of the function f of x comma y is equal to x y minus x square minus y square minus 2x minus 2y plus 4. So here the given function is f of xy is equal to xy minus x square minus y square minus 2x minus 2y plus 4. Now for the critical points, we have to find the partial derivatives of this function with respect to x and with respect to y and equate them to 0. So first we find partial derivative of del f by partial derivative of f with respect to x, which is del f by del x. So it is partial derivative of x is 1 and y remains as it is. So y minus 2x minus 0 minus 2 minus 0 plus 4. So we get del f by del x is equal to y minus 2x minus 2. So let us see. Y minus 2x minus 2 is equal to 0 and equate this partial derivative at 0 to find the value of the point. Okay, so this is y minus 2x minus 2. Now here we have to find out and equate del f by del y to 0. So we can find the partial derivative of f function with respect to y. So del f by del y, so differentiation of this y is 1, x remains as it is, so this is x, then minus x square is 0 because we are differentiating this with respect to y, and the partial derivative of y square with respect to y is 2y, so this 2y, and this is 0 because we are differentiating partially with respect to x, and minus 2y's partial derivative with respect to y is minus 2, and this is 0, so we don't write 0 here, and it is equal to 0. So we need to find the value of x and y which are satisfying this equation 1 and 2. So for solving 1 and 2, we take 2x minus y is equal to minus 2, or we can say y is equal to 2x. We have first equation y minus 2x minus 2 is equal to 0. That means y is equal to 2x plus 2. Substituting these values for y is equal to 2x plus 2 in the second equation in this equation, so x minus 2 into 2x plus 2 minus 2, so we get this x minus 2 into 2x plus 2, so 2 into 2 minus 4x, and this is minus 4, 6, so we get x is equal to minus 2. And if we substitute the value of x is equal to minus 2 here, so 2 into minus 2 minus 4 plus 2, so again minus 4 plus 2 is minus 2, so we get the value of y as minus 2. Therefore our point is only minus 2 comma minus 2. So this is the only one critical point for the given function. Now to check the nature of the critical point of the function, we need to find the second order partial derivatives at the point AB, or at the point minus 2 minus 2. So we need to find second order partial derivatives. So del square f by del x square is the partial derivative of del f by del x with respect to x. So let us see the partial derivative of f with respect to x is this. So if we differentiate this partially with respect to x, then this is 0, and this is minus 2. Okay, so del square f by del x square is minus 2, so it is this minus 2. Then we want to find del square f by del y square, so it is again minus 2. So del square f by del y square is the partial derivative of this equation 2 with respect to y. So this is 0, and minus 2. So let us see. Del square f by del y square is equal to minus 2. And this del square f by del y del x is the partial derivative of del f by del x with respect to y. So we take del f by del x, this one, and differentiate this partially with respect to y. So this is 1. Okay, so del square f by del y del x is 1. So it is this one. Now at the point we have to find out the value of del square f by del x square is equal to minus 2. Del square f by del y square is equal to minus 2, and del square f by del y del x is equal to 1. If we substitute xy is equal to ab, then this value remains as it is. So del square f by del x square at the point minus 2, minus 2. Our point is minus 2, minus 2. Where is it? Yeah, this is minus 2, minus 2. Minus 2, minus 2. So this is minus 2, minus 2. Here minus sign is there. Okay, here also minus sign. So r, which is del square f by del x square, is equal to minus 2. Similarly, we find t, which is second order partial derivative with respect to y. So del square f by del y square at the point minus 2, minus 2 is equal to minus 2. And s is equal to del square f by del y del x, which is at the point minus 2, minus 2 is 1. So now rt minus s square. So rt is minus 2 into minus 2, minus 2 is multiplied by minus 2 is 4, minus 1, so 3. Okay, so rt minus s square is this 3 greater than 0. Therefore function has either maximum value or minimum value at this point minus 2, minus 2. But if r is we have to check the value of r. So r is minus 2, so r is less than 0. So the function has a minimum value, not the minimum but the maximum value at this point, f at minus 2, minus 2. This is maximum value. Okay. Now we take another method to find the extreme value, which is known as Lagrange undetermined multiplier. So in this method, one function is given with the constraint g of x, y, z is equal to c, or g of x, y, z, c is equal to 0. And we want to find the extreme value for the function u is equal to f of x, y, z with the constraint or with the condition this. So we formally discuss the method. Let u is equal to f of x, y, z be a function of 3 variables with a condition that g of x, y, z is equal to c. So for the function u, which is equal to f of x, y, z, to have an extreme value, the necessary conditions are the partial derivative of the given function are zeros. So here del u by del x or del f by del x is equal to 0, del f by del y is equal to 0, and del f by del y is equal to 0. So clearly we can say that del f by del x into dx plus del f by del y into dy plus del f by del y into dz is equal to 0. We denote this equation as equation number 1. Now we have the another condition, g of x, y, z is equal to 0. So if we differentiate, or if we find the total differential of this function g, which is denoted as dg, earlier we have defined how to find or what is the total differential of the given function. dg is the total differential of the given function with, so dg is equal to, and it is defined as del g by del x into dx plus del g by del y into dy plus del g by del z into dz, and it is equal to 0 because dg is equal to g is equal to constant. So after, if we take total differential of this, then it is 0. So let us write down, since g of x comma y comma z is equal to c, so dg total differential of this function is equal to 0, and this dg is defined as del g by del x into dx plus del g by del y into dy plus del g by del y into dz. This is z again. Del g by del z is equal to del g by del z into dz is equal to 0. Okay, now we have this dg is equal to 0 and df is also 0. This is also total differential. This is del f by del z. So this is total differential df, and dg is also 0. So we can multiply this equation by lambda and add it to the equation number 1. So we can say that df plus lambda into dg is equal to 0. See, let me show you. Df into lambda dg df plus lambda dg is equal to 0. So we get this df plus lambda dg is del f by del x plus lambda into del g by del x dx plus del f by del y plus lambda dg by del y dy plus del f by del z plus lambda into dg del g by del z dz is equal to 0. This is what df total differential of f, and this dg into lambda is the total differential of g times lambda. So here lambda is a parameter called Lagrange's multiplier. That is, sometimes we require to find the value of lambda, but it is not necessary to determine in each case. So this is the okay. Now this equation 4 implies this is equal to 0, del f by del x plus lambda into del g by del x is equal to 0, del f by del y plus lambda into del g by del y is equal to 0, and del f by del z plus lambda into del g by del z is equal to 0. So these are the equations, and they are denoted as equation number 5, 6 and 7. So we can solve equation 3, no, not 3, equation 2, g of x y z is equal to c, and then 4, del f by del x plus lambda into del g by del x is equal to 0. 6 is this, del f by del y plus lambda into del g by del y is equal to 0. This is 6 one, and del f by del z plus lambda into del g by del z is equal to 0. So by using equation number 2, solving equation number 2, 5, 6 and 7, we can find the point or find the value of x, y, z, and it will be either maximum value or minimum value, because we have taken lambda in such a way that the function will have an extreme value. It may be either maximum value or minimum value. So that is to be determined with the help of finding or comparing the value of function at different point at the given point. So let us take one example. find the extreme value of the function f of x y is equal to 3x plus 4y subject to the constraint x square plus y square is equal to 1. So we have the function 3x plus 4y, and this function domain is in such a way that x square plus y square is equal to 1. So we can take the value of x and y in such a way that x square plus y square is equal to 1 for the function domain of the function f of xy is equal to 3x plus 4y. Now here the function is 3x plus 4y, and the given condition can be written in form of g of xyz minus 0, x square plus y square minus 1 is equal to 0, which is denoted as g of x comma y comma z. So here only two variable is there, so we can write down g of xy is equal to x square plus y square minus 1 is equal to 0. By using the method of Lagrange's undetermined multiplier, we can find out two conditions, del f by del x plus lambda into del g by del x is equal to 0, and del f by del y plus lambda into del g by del y is equal to 0. Now f is 3x plus 4y, so del f by del x is 3 and del f by del y is 4, because the f is 3x plus 4y. See, 3x plus 4y. So if we differentiate this, then del f by del x is 3 and del f by del y is 4. So let us see. This is 3 and this is 4. Now g is x square plus y square minus 1. So del g by del x is 2x. So this is 2x. And del g by del y is equal to 2y, because g is x square plus y square minus 1. Partial derivative of g with respect to x is 2x, and partial derivative of g with respect to y is 2y. Okay, fine. Now we have these two equations, 3 plus lambda into 2x is equal to 0 and 4 plus lambda into 2y is equal to 0. So these are the equations second and third, and solving second and third for x and y, we can find out x in terms of lambda. Okay, so x is equal to minus 3 by 2 lambda. From here x is equal to minus 3 by 2 lambda, and from this equation we get y is equal to minus 4 by 2 lambda. So 2 is cancelled out and we get minus 2 by lambda. So after finding this value, we have to remove this lambda, or we have to decide this lambda so that x and y is the fixed value. So here lambda is parameter and that is to be determined first. So we have the condition on x and y, which is x square plus y square minus 1 is equal to 0, or even you can say that x square plus y square is equal to 1. So we substitute the value of x and y. So minus 3 upon 2 lambda whole square plus minus 2 upon lambda whole square is equal to 1. So from this equation we get 4. We can simplify this and get 4 lambda square is equal to 25. See, this is 9 upon 4 lambda square plus 4 upon lambda square. So 4 is LCM, so 4 will be multiplied here. So 9 plus 16 upon 4 lambda square. So it is 1. So 25 upon 4 lambda square is equal to 1. So 4 lambda square is equal to 25. So lambda is equal to plus or minus 5 by 2. So lambda may have the two values, plus 5 by 2 or minus 5 by 2. So we have 2 points, minus 3 by 5, minus comma minus 4 by 5, or this is the point xy as minus 3 by 5 minus 4 by 5, or we can say that xy as another point 3 by 5 comma 4 by 5. Now according to the method, this point is either maximum value and this point function has a minimum value or maximum value that can be determined by using some conditions. So clearly we have 2 points, minus 3 by 5 and minus 4 by 5, or 3 by 5 and 4 by 5, at where the function has extreme values. Now we have to determine whether function has maximum value or minimum value at this point or at this point. So for that we find out f of minus 3 by 5 comma minus 4 by 5. So if we substitute this value, 4x is equal to minus 3 by 5 and minus 4 by 5 in this, so yeah, in this minus 3 by 5 and 4 by 5 is to be substituted. So we get x is equal to, okay, f at this point is equal to minus 5 and f at this point 3 by 5 comma 4 by 5. If we take nearer point 0 0, then it has 0 value. So this is lower than 0 value. If we find out f of 0 0 nearest to this point, we can find the point near to this point. Say 0 0 is the near to this point, so f of 0 0 has the value 0, so which is more than this, so this is smaller value, or even you can say that the smallest value near to this point or in the neighborhood of this point. So f of minus 3 by 5 comma minus 4 by 5 is equal to minus 5 is the minimum value, and if we find f of 3 by 5 and 4 by 5, then it is 5. So if we compare with the value of the function at another point in the neighborhood, then it is 0 0 is in the neighborhood, so f of 0 0 is 0, so which is less than that. So this is bigger value compared to the value of the function of a point in the neighborhood of this point. So it is, this point will be the maximum value. So this way we can observe that the function f minus 3 by 5 comma minus 4 by 5 is equal to minus 5 at this and has a, so this is the, this way we can decide function has either maximum value or minimum value at this point. So today we have discussed about method of finding maximum and minima of a function of two variable, and another method which is known as Lagrange's undetermined multiplier to find or decide the extreme value of the function. So you can practice some more example to find the maxima and minima of a function, and take some example on Lagrange multiplier. Thank you.